Okay, so we are going to consider an interesting example. So by the way, today I'm recording this video on uh, September 2nd, and today my son went to kindergarten for the first time. He had the first full day in kindergarten. I'm so glad he he started kindergarten. Anyhow, so this is I made up this example when my wife was pregnant, had my son like 5 years ago, and at the time, so you know that there are some birth defects. So birth defects are, say, genetic abnormalities or other some defects that happen at like that the baby has at birth. Also, and there are some medical screening tests for those defects. So you can tell if your baby has uh, defects or not. But examples of the birth defects include Down syndrome and spine or brain problems or heart problems, and like every part of the body may may have some defect. And and so if you do some screening test, you may get positive result, which means high risk of birth defects. And during my wife's pregnancy, I we got a positive result. It was quite early in the pregnancy, and it's really heartbreaking. So uh, I and it's by the way, but positive results does not imply it sure anything for certain. So in medical studies, diagnosis and screening are different. Diagnosis is a confirmation. It's 100%. It's a certain result that confirms the presence of some medical condition. So if you are diagnosed with something, then you do have that. But screening is more like a random thing. It's uncertain. It's not 100% sure. It only detects risk factors or some signs of potential problems, the not a confirmation of the problem condition. So yes, when we heard when you heard the positive result, it was we were really sad and very scared. I don't know what would be what our life would be. But in the end, it was nothing. He's totally fine. But and I will tell you, you don't need to be worried. It sounds like the doctor tells you like as if it's a super serious problem, but actually not. I will tell you in case if you encounter a similar uh, situation. Okay, let me write defects as D and P for positive result, N for negative result. And say, like me, suppose that my baby got a positive result. So then, what is, but so that's, so the what is the probability that your baby does not have any birth defect, given that your baby got a positive result? What is the probability uh, your baby is fine, does not have any defect? The answer is C. The condition is positive result. You already know that, and it happened. Given that we are interested in the probability of having no defects, so C is what we would like to calculate. That's the probability we want to calculate. Uh, so this is what we want, and then now, then it's my experience. in the doctor's office. The doctor told us the positive result and explained how accurate that is. Explained this is an up-to-date, very advanced screening test, so it is super accurate. I don't know why she did. It sounded like she tried to scare us. So she said the probability of the positive result when birth defect exists, it's like 99%. That is called detection rate. Detection rate. So when defect exists, the outcome comes positive. This probability can be also written in our notation. What is that? What is the detection rate? Think about that. So this is now different because the condition is when your baby has a birth defect, that's the condition. If you assume that, what is the probability that the result comes positive? So given D, what is the probability P? So the answer is B. This is the detection rate. And the doctor tells us a lot about how good the detection rate is. It's nearly like 100%. But think about the situation. We are in this situation. There are four different scenarios. Your baby has a defect or not, and the result comes positive or negative. And among the four outcomes, only two are true. I mean, the results are correct. So when the baby has a defect, the positive result is a correct result, correct test result. So we call it true positive. But if the result may be negative, then it's a false alarm. I mean, it's not an alarm. So it's false, wrong. The result was wrong. Similarly, if your baby does not have a defect, negative result is the correct test result, and positive is a wrong test result. So in this way, two are correct, two are wrong. And in statistics and medical sciences and other fields, biostatistics, try to measure, find a good measure that summarizes the accuracy of this test. How accurate, how many times it is correct rather than wrong. So they defined detection rate or sensitivity rate. So depending on the fields and subjects, they call it different ways. I don't know why. So detection rate or sensitivity rate is defined as probability of positive result when it should be positive result. So when the baby has a defect. So probability of correct positive and specificity and selectivity, right? I don't know why the names are like this, but anyhow, it is the probability of conditional probability of true negative given no defect. So now you can imagine that this is how researchers or scientists do their experiments, right? They collect sample, like say, I don't know how they do it, but like say genetic samples from babies with defects, and they try some screening test and see how many times it turns positive. That is detection rate. So in the lab, this is what you get, right? You already know you collected sample, knowing the result, and try the test. But you are doing the other way. You do not know whether your baby has any defect or not, but you already observed positive or negative result. So we are in the same situation. Like we have to change the role of main event and condition. So we have to switch the conditional probability. That's what we are going to do. Let's think about more detailed numbers. It's so you may think it's extreme, but this is what my doctor told me. detection rate is 99%, and specificity rate is 90%. And we are going to additionally assume that birth defects happen to 1% of babies. Suppose that that is known. Suppose that 1% of babies do have birth defects. As you see, the numbers are quite extreme. And now I will let you do it first. So you may use the tree diagram method, as I showed you earlier. And I recommend you to use 10,000 as the initial number. So think about this. You have 10,000 genetic samples from babies. Some of them may have birth defects, some of them may not have birth defects. Use the tree diagram method to classify 10,000 genetic samples into four outcomes, four categories like this. Use this information and find the number for Z. So do it by yourself on paper with your pen, and it will be fun to make a simple tree diagram. Okay, I'm going to stop the video here. Please do the work and choose your answer, and then watch the next video. Thank you.